I've just bought this Align Trex 700E helicopter. I've played around quite a bit with multicopters, even planes a little, but I've never had a good radio control helicopter. So my plan is to get this flying and to put an ArduPilot flight controller on it. I bought it from a local guy as a bare skeleton. It didn't have the servos installed, no gyros or batteries. So my objective is to figure out how radio control helicopters work, put it together, fit all of the electronics I need, and then see if we can get it flying. I've just been installing the servo motors. As you may know, helicopters use a swash plate, and in this configuration there's two servos which function as the ailerons, and one additional servo which is effectively the elevator. So in order to get the servo horns put on in the right phase angle, I've got a servo tester, and I can use this to set the servos to their neutral position. And when they're in their neutral position, you want to make sure that the horn is oriented so that the control arms are perpendicular to the axes of the servo. Now the guy I bought this off obviously already had this pretty well set up, and so I've got it set up so that when the three servos are in the neutral position, the swash plate is fairly level. At the moment I've just got this hooked up to the elevator, and you can see if I set it on cycling, then you can see the swash plate respond. To run ArduPilot, you also need flight controller hardware. So in addition to the CPU, that board also contains the accelerometers and the gyros, and then you also use compasses and a GPS. So looking at this fuselage, there's nowhere obvious to mount that hardware. The compasses and radio receivers should be away from sources of interference and magnetic fields, and of course you've got the main drive motor right here in the middle. Also there's physically just no obvious spot. So I designed these simple platforms with a clamp which can go around the tail section, and I think given that none of this equipment's very heavy, I don't think it should have any significant effect on the centre of gravity, but it gives us somewhere convenient and accessible and also away from the magnetic fields in order to mount this hardware. So I've already mounted the flight controller, the telemetry radio, and some other bits of equipment, and then I've got another board in the cover, a fairing made up, which I'll mount behind that, and that will have the compasses as well as the radio control receiver. I have uploaded this project to Thingiverse, by the way, so if anyone is undertaking a similar project, those files are available for download and 3D printing. I've now done the basic install of ArduPilot onto the flight controller, including all the regular well-documented steps like calibrating the accelerometer and the compass. One of the things that I did remember is that the servo motors I have are 6-volt servos. Maybe that's common for large helicopters so that you get the extra torque. Fortunately, in my case, the Martech flight controller board does have a hardware jumper that lets me set it for 6-volt operation. Also just remember that for some of the calibration steps, it really doesn't matter where the landing skids are. Rather, it's essential that the shaft is perpendicular to the ground for setting the level position in flight. I measured the distances between the contact points on the swash plate and confirmed that they're equally spaced or 120 degrees apart. So I have ArduPilot configured for the H3 120 swash plate, and I've just wired the 3 servos up according to the instructions. And so just to verify that this is all set up right, if I push the elevator forward and the swash plate tips forward, elevator back, roll left, roll right, and then collective down and collective up. The ArduPilot traditional helicopter website has a good tip on levelling the swash plate using a magnet and a nail, or I'm using an Allen key. The basic idea being that we fit the magnet to the shaft,
adjust this straight edge so that it just touches the top of one of the 3 control arms, and then we rotate the shaft and just check that it's got the equivalent clearance or is just touching the top of each of the 3 control arms. If you find that's not the case, if you find one of them is a little too high or a little too low, then you can adjust the servo trim parameter in ArduPilot in order to get that swash plate in a level neutral position. The next thing on the list is to set the maximum and minimum pitch for the collective. So this sets the maximum climb rate and descent rate. Because I don't want to do 3D flying or acrobatics, all the numbers online suggest I set the maximum pitch to about 12 degrees and the maximum down pitch to about -2 degrees. Of course, you can buy pitch gauges online. I actually found this nice little model on Thingiverse and 3D printed it. So this snaps around the propeller blade. You fit your mobile phone to use as a spirit level, and then you can use that to adjust the relevant parameters in ArduPilot until you're getting the 12 degrees, -2 degrees that I'm looking for. Naturally, you will want to check the pitch on both of the blades, and you also want to check it at a number of different orientations. If you find that one blade is systematically different, then you might need to adjust one of the control linkages, or if the pitches are consistently different in one part of the revolution, then there's probably a bit of iteration that needs to happen with your swash plate leveling. You might need to go back and adjust some of the servo trims a little further. Time for a sanity check at full flight revs. One thing I hadn't set up yet was the servo motor for controlling the pitch of the tail rotor. In fact, when I tried initially, I couldn't get the servo to move at all. Then the guy I bought it from gave me the helpful tip that tail servos are often super narrow band, so they need to run with different pulse width parameters to most servo motors. So knowing that, it was just a matter of setting the max and the min pulse widths to give me the range of control I wanted, and setting the trim value to make sure that the rotor rests at a neutral position where it wouldn't generate torque left or right. Naturally, you do want to check that it operates in the correct direction, and I did find that I needed to use the checkbox to reverse the direction of operation. So before attempting the maiden flight, I just need to check that the centre of gravity is directly under the main shaft. And of course you can adjust the distribution of your batteries to make sure that is the case. Time to see if this thing flies. It is a lot windier than I would like today, but I found a spot that's quite sheltered from the wind. It also has a fence all the way around it, which might be a good thing or a bad thing depending on how this goes. My main objective for these first flights is firstly just to see if it is stable in stabilised mode. And if that's the case, then I'd like to hover for a little while, just so I can measure the vibration and tune the harmonic notch filters. Well, it flies. It was controllable, didn't try and flip upside down and crash, so that's always good. It was a lot more twitchy than I expected up and down, so I didn't feel confident trying to hover for any extended period, especially in this wind. Nonetheless, I'm keen to use even just a few seconds of data to get initial values for the harmonic notch filter. So zooming in on the gyro noise, you can see the fourth harmonic, the second harmonic, and the fundamental of the rotor frequency at around about 33 Hertz. So the harmonic notch filter uses digital signal processing to remove the effect of vibration from the accelerometers and the gyros. It's really well documented on the ArduPilot wiki pages. I will go through this again after I do a longer hover, but at least this way I've got some initial values in there, so when I try and take off for the next flight, it will have the first order approximation to removing that noise. The main thing that caused me problems on that first flight was that I found the controls for the collective to be really touchy, and I couldn't easily hold it at a fixed altitude. So looking at the log file, the rate commands for the collective were oscillating around the 0.42, 0.43 mark. ArduPilot does let you specify the curve that maps the control stick position on the remote through to the actual collective being requested. At the moment I've got no interest in using the extreme minimum or maximum of the range of collective that's available, and in fact what I want to do is flatten the control curve out around that sort of 0.4 number that I identified from the log file. With those changes done, it was a lot easier to fly on the second attempt, even though there was still a bit of wind around. I also got to the point of doing a takeoff and hover in pods hold mode, where it uses the GPS to maintain position automatically. So far I've just been flying with the default PID and other tuning parameters. Looking at this graph of the requested versus the actual response of the helicopter for pitch and roll, pitch looks pretty good actually, but there's clearly room for improvement in roll, and in any case, to get the helicopter flying at its optimum level, then I want to tune all of these parameters. You can do this manually. While I've never used auto tune for a helicopter, I think that's the route that I'll take, and once again this is well documented on the ArduPilot wiki. Well folks, I hope some of this has been useful to you. For me really it's just been about documenting the learning journey with setting up the helicopter and the traditional helicopter build of ArduPilot on that machine. Thanks very much for watching. Post a comment if you've got any further input that might be useful to others.